And one and two and one, two, three. Hello guys, how you guys doing? Yep. Hello guys. Hi. Hi guys. Hi guys, how you guys doing? Today we have a really interesting topic that we're gonna be discussing. It kind of ties to my research in some aspects, and it is one of a very interesting breakthrough that has happened in the AI field. So I feel very excited to share that with you guys today. So, as you can see, the title that we have for today is AI has left 2D forever, and why does crypto actually need it? Just waiting and waiting on a few people to see if the stream is working, and then we can go live and start sharing our insights. It's kind of cool today. I woke up a little bit early and it's a little chilly, but it's nice. Early mornings are actually nice. I like that. Just kind of cozy. I made up my bed, and it just feels kind of interesting that you can kick off your day like fast, and you can just do the most engaging and most rewarding part first. So I just hopped on the stream for you guys. Looks looks like it can be rewarding and actually helpful. Just let me check once if the stream is working. Amazing. Hello, guys. So, as we were discussing, the title of our today's discussion will be based heavily on why AI has actually left the 2D world forever and all the things, the major important breakthrough that has happened that has which has enabled AI to actually leave the space for good. And why does actually crypto come into the picture, and how do these two modalities have become more intertwined than we can actually imagine, and how do we see the future coming out, uh, future playing out in the coming future. So I've been thinking about flatlands all morning. If you look at the last 10 years of AI, we built a genius we built a genius machine that lives in two dimensions. We have fed it billions of images. It became incredible. It has become incredibly efficient and incredibly good at reading the pixels, understanding colors, and recognizing our faces. As we all know, we all use Apple phones, all this different stuff. So we know that they have become extremely efficient and good, accurate at all these different tasks. But it was trapped. It had no concept of a volume. It, the AI, I mean AI, which is AI, it did not know that if I hold this phone, right? If I hold this phone up here, there's a backside to it. It just saw a one simple rectangle. So this week, that has totally changed forever. And I don't think people even realize that the scale of the shift because of this news cycle is so noisy. It's so noisy right now. People don't know what impact it is gonna have on our fucking world. Meta, or ex Facebook, just released SAM 3D, the segment anything model for 3D. Most people see this and think, cool, better tool for video games. I see this and think this is the indexer for the physical world. I'm a monk, as you all know, and I'm researching on this topic for the last few years. And I work at the intersection of computer vision, and I'm also exploring tokenization, which is the financial system is going heavy into right now. So that's one of my two hobbies and passions, and I've been working on that for a second, and I am today I want to take you through the technical breakthrough of SAM 3D and share my perspective on how it's going to change the world. Why Mark Zuckerberg is basically colonizing reality while everyone else is fighting over chatbots and the massive huge financial implication that this has for crypto and the real world assets, or in short RWAs. So to understand the breakthrough, we have to look at the hierarchy of computer vision tasks. In my field, we usually divide vision into three levels of intelligence. Level 1 is classification, the basic. The AI looks at an image and says, car. It is a car. It is a box. It is a train. That is vague. It knows what is in the image, but not where. So it's not that smart. Level 2 is detection. Okay, I know that this is a car, this is a train, this is a box. The AI draws but the task of detection is to actually draw a box around that object. It says the object or the car is exactly here in this particular screen. This is what self-driving cars use to avoid hitting pedestrians and other objects in the scenario. It's useful, but it's boxy, it's crude, it's 2D. Level 3 is segmentation. This is God mode. The AI identifies every single pixel that belongs to that particular object: the curve of the bumper, the glass of the windshield, the rubber of the tire. It separates the signal from the noise. Now we conquered level 3 in 2D. Years ago, there has been improvements happening. SAM, which was also released by Meta, was released like 2 years ago, and they have been building a foundation model on this for past couple of years. But this work has been going on for segmentation, particularly in 2D, and the basic problem was kind of solved to a decent extent some years ago. But doing it in 3D, that was the bottleneck. So to get a 3D model of this room where I'm sitting, I used to need a LiDAR is a scanner, which self-driving cars also use. Some self-driving car companies like Waymo use, uh, where I had to take about like 100 something photos from every single angle and run through photogrammetry, which is a computer vision algorithm, photogrammetry software, and it was slow, it was expensive, and it was totally unscalable. So so what did Meta actually build with SAM 3D? What was it able to achieve with SAM 3D, and what is it even about? They built a single view reconstruction engine. Technically, this is a massive leap. They are using a generative approach to hallucinate geometry. They actually do not know the 3D object, but as humans, when we see the idea is, as humans, when we see a 2D object, we are able to decipher what the object in 3D would look like. Just because of years of training and our analysis and perception of the world, we are actually about right almost 95% of the time, at least, right? So Meta drew on the same principle that why can't a machine do the same thing while observing a 2D object? Can the machine itself perceive the 3Dness of the object, seeing countless number of examples, like a human, that it can use to learn at the time of training? So it works like this. You feed it one single image, that like a flat image for, let's say, a car or a shoe or a monitor or a box or a train, but we show it a flat image. The model uses the term called priors, which is a common word in machine learning community. Priors, which is a prior knowledge essentially. Prior prior knowledge. it has from seeing millions of other box images, car images, shoes to predict the 3D shape, the texture, and even the parts of the object it cannot see. So it just sees a 2D image and it's using the prior history of understanding from previous examples it has seen. It will be able to ex- pretty accurately predict the 3D shape, the texture, as well as the parts of the object. Let's say a car it has not seen in the particular example. So what does it even solve? It essentially solves the occlusion problem. What is occlusion problem? In the real world, things block other things. If I am sitting on this chair, I'm blocking this chair. Maybe some part of this chair is actually visible, but just by looking at the 2D 2D projection, you are not able to see the chair wholly. So that is the occlusion problem. But see from as human minds, looking at me in this 2D scene and looking at some partial view of this object, this chair, you can pretty much hallucinate, or you can predict how the 3D object, this chair, would actually look like if you would have to see it. So that hallucination is the same principles that SAM 3D draws upon. So in the real world, of course, the things block other things, uh, and if a cat walks, let's say for example, if a cat walks behind a table, a 2D AI thinks that the cat ceased to exist. The SAM 3D understands that the cat still has volume and a coordinate in space even when the cat is hidden. And the killer feature, it is this module is promptable. Just like you type a prompt in ChatGPT, you can prompt SAM 3D with a click. I can show it's a messy 3D scan of a room. Uh, if you can see on the screen, I'm sharing on my screen, and there's a 3D room. Uh, uh, it's a messy 3D scan. There's clutter there. There's multiple objects, right? And it's just points. This is a 3D point cloud, by the way. That's the way how things are. That's the way of a data representation of a 3D module, 3D object. Uh, it's just points floating in the void. Connecting those points into a meaningful object, semantic understanding is what they just solved. So now let's zoom out. Why is Meta giving this away for free? If this tech giant is so good, why is the code available on GitHub for free? You want to know the real answer? Because Mark Zuckerberg is actually playing a totally different ball game than Jensen Huang at Nvidia. Nvidia sells the shovels, the H100, the H200s, the Blackwell, etc. Meta wants to own the land. The land the land which is used by the shovels, but Meta is gonna own the whole land. Meta has a data problem. To build the metaverse, the sole reason they changed their name from Facebook to Meta, which is the huge bet they took 3 to 4 years ago. They have not given up on that. They knew when they took this bet that this is going to be a huge thing, and it's only about time when people adopt the Meta's vision. So the Meta right now is facing a data problem. To build the metaverse and make the Orion AR glass useful, they need a 3D internet. But the current internet is 2D, as we generally see things on a screen, and that's how we interact with the world generally right now. So they released SAM 3D to turn us into the workers by giving us the tool to convert 2D images into 3D assets easily. We populate their database. We build the 3D internet for them. for free. They could not have done this even by hiring 100 actors, 1,000 actors, because it's just not enough. So they outsourced it by making the base model, the platform itself free. So when the creators onboard it, they can use the data that the creators develop for free, because they are not monetizing the platform itself, but they're capitalizing actually on the data, which is the real gold here. Um, so they're they're essentially establishing the standard with every medical scanner, every robotics company, every crypto protocol has been built on SAM or Meta's framework. Meta owns the operating system of reality. It's such a big thing. It's such a big thing. It is the classic strategy: commoditize the complement, make the software free so the value accrues to the network. Meta is amazing at this ball game. They did the same thing with FB. We use Facebook, we use WhatsApp, we use Instagram, all for free for general purpose users. But the thing that they actually have moat on is the data itself. So Meta knows how to play it really right and really lead in this particular state of mind, and how do you capitalize actually on by freeing the network and capitalizing on the data itself. So, this brings me to the massive opportunity for crypto. I talk a lot about RWAs, real world assets, tokenizing real estate, luxury watches, vintage cars. But there is a flaw in that thesis: verification. If I sell you a token that represents if I sell you a token that represents this phone, right? If I sell you a token which represents this phone, how do you know this phone is real? How do you know if it's not scratched, it does not have any marks? How do you know if I didn't swap it for a fake? I've bought a fake phone which looks like an iPhone but it is not. How would you know if I'm trying to sell you an asset for this phone? A PDF certificate is not enough. PDF certificate is, and again, a document. First of all, most people don't want to read it. Second, how would that be a justification that this phone is actually real in 3D in real life? Not on a screen, but in real life. This is tangible. This is actually has value. SAM 3D is the verification layer here. With this technology, we can scan an asset with a simple phone camera from some angles. Maybe single angle will also work, and we can segment the specific wear and tear, that the scratches, the unique angles of how the phone looks. Maybe the phone is getting old, the unique dents, if the phone has taken some damage in the past. And we can create a high quality, high fidelity digital twin of this asset that acts as a 3D blueprint, or 3D fingerprint, particularly, essentially. So this can we essentially will build a 3D fingerprint of this particular asset, and we will do it for every single 3D object that's present in the world. Imagine, just imagine, just imagine how big this thing is. Instead of actually just seeing the object and me promising you the asset on face value, that this is a thing, just take it. I cannot decipher on the object is actually how the object value is changing with time, based upon its 3D reconstruction and uh, understanding of the world we have when we just see a 2D object. We're able to create a 3D artifact by 3D model, just by looking at from a few angles, and we can basically generate a 3D rendering that essentially dictates the value of the object in the real life, and that can be directly used to tell you as as a buyer what is the value of this object in real time at a certain point in time in life. that that is huge. If you understand, if you see my perspective, this is huge, huge. We can hash this 3D data onto a chain. So if I try to sell you a fake, the geometry won't match. If I sell you a fake, the geometry won't match, or the examples are not certified. We can. I'm pretty sure there's gonna be a next model uh, where the 3D object, which is a real one, will have a certified 3D model from the or 3D model given by the company itself of how a real 3D model looks like. Maybe there will be some 3D signature or like fingerprinting that will happen on a real object, like a holographic 3D fingerprinting of that this particular brand has this particular uh, for example, watermark, essentially a 3D watermark. That's what I'm saying. And you can verify a fake from a real by just clicking a few pictures, and the 3D reconstruction will essentially match the 3D watermark, and that will be an amazing way to actually validate if this is fake or not, and how this object's value is changing over time. This is unprecedented, remarkable, new, amazing technology that's just on the horizon, and it's going to change how we interact with the world. If I try to sell you a fake, the geometry would not match. The 3D fingerprint would fail. You cannot have a decentralized economy without eyes that can measure the world. So the SAM 3D gives the backbone. SAM 3D actually gives you a strong backbone to look at a 2D, to interact with the 2D, but see actually interact with the 2D in a more 3D, in a 3D space, and you can basically visualize a 2D into a 3D, and you can make good and real world grounded judgments based upon the reconstructions that the SAM 3D model actually enables. So you can make good judgments based upon these. Uh, so you can make good judgments on the 2D world using this 3D reconstruction, and you can interact with the world much more cohesively and in a grounded manner. You will trust the system more. So the opportunity and the uh, valuing of the particular object or a commodity is just gonna be amazing. It's just gonna be a new paradigm of how we interact and uh, how we judge a value of an object, and how we interact with the uh, objects and the different uh, goods that are being sold by different players in the market. So the future isn't just about generating text. It's about digitizing reality. We are moving from an era where computers guess what the real world looks like to an era where they can measure it, understand it, ground it, and verify it. If you are a developer, stop. If you're a developer, stop building another wrapper for ChatGPT. Start building applications on SAM 3D. If you are an investor, look for the protocols that are using SAM 3D to verify assets. I'm going to be testing this model to see what all remarkably other things it can do. I'm also gonna show and go into post another video which will go a little bit more into the technical insights. Technical insight. I'm gonna show and post another video which is gonna go a little bit deeper into the technical insights of this paper, and the link will be posted soon on my channel. I'm Umang. Thanks for watching, and peace. उड़े जो दिल की पतंग से, उड़े हैं वो याराने, जिंदगी के। Amazing. Okay, looks like we are live now. So now we'll be going deeper into how the SAM 3D actually works and what are the implications of this new technology. So SAM 3D was recently released by Meta, as we were discussing, and it clearly says, and it clearly says, SAM 3D can bring any 2D images to life, accurately reconstructing objects and humans, including their shapes and pose. They have a playground option here, which you can use to try how their model actually works in real life. You can download the models that they have and use that as free as you want. I think they have an MIT license, so you can use it for free for at least non-commercial uses. And if you can see here, it just took this picture of this object and it literally created a 3D object of this particular 2D image. You click this tennis player and they literally created a whole full 3D rendering object of this person, which is amazing. This is unprecedented. For each object in the scene, you have a 3D object that you can bring out just by clicking a 2D object. You just click this 3D scene, it will sample different objects in the scene, and once it knows it's this object, it will make a 3D rendering of that, which is remarkable. Again, The models that they have shown, that they have published, are for different objects. So there is SAM 3D objects, which is generally for single image input. It's detailed 3D reconstruction of any masked objects, including geometry and texture. Independent post 3D models will be generated, and it's suitable for manipulation, interaction, etc. And reconstructions are robust to occlusions in the input image, which is huge. We'll discuss how that is made possible. And it uh, the position it positions multiple objects into a scene jointly with SAM 3D body reconstructions. So it will be like a full joint 3D model all at once. The same thing with SAM 3D body. We just give it a single image input. It reconstructs body shape and pose, including unique positions and partial visibility, and it still creates 3D models for each of this person. Suitable for manipulation and interaction, promptable with joint reconstructions, position multiple people into a scene jointly with SAM 3D object reconstructions. You can use this for Facebook Marketplace, which is one of the really high utility cases that they're showing here. Uh, you can experiment with different models. They will go into the model architecture in a second. They have basically two type of models: SAM 3D body and SAM 3D objects. Uh, they are almost pretty similar in their architecture that we will discuss. Just a final block change that they have done for two different types of modalities, which is body and objects. And here they go into the state of the art performance that they have published in their latest paper, and the results look pretty phenomenal actually. So on 3D shape and scene reconstruction performance, just from a 2D object, mind me, uh, the F1 scores are much higher than the previous amazing models that people have used. Uh, so Hunyon is a 2D, Hunyon 3D is it again a 3D reconstruction model plus foundation pose is probably a layer on top of, you throw on a 3D model generator to get each object. Uh, Probably some other models that have come out in this area, and the F1 scores of SAM 3D objects is significantly higher. Uh, the 3D IOU of the layout is decent, is 0.42, and yep, we'll go deeper into what this metric even means. 3D shape and texture preference test. So the mm, so 90% of the time, SAM 3D objects are preferred over the shapes and textures generated by all these other models, which kind of highlights that SAM 3D objects is actually doing a better job than all of these models. If we go here, that's for 3D human mesh recovery performance. So for 3D body objects, human body mesh, and the all these different metrics that go on that are elucidated in the field of 3D pose estimations and all 3D reconstruction are just here. And as we can see, SAM 3D basically outperforms all these previous models by a huge margin. Um, the 3D human mesh recovery preference test. The model here is again the same thing. So the times when SAM 3D model is outperforming is much higher um, compared to other models, and NLF is pretty much equal to SAM 3D, but other networks SAM 3D is generally more preferred than the models that are used for human mesh recovery from 2D objects. And on top of this, they have published a dataset of diverse and high quality 3D meshes. A new first of its kind evaluation set for visually grounded 3D reconstruction in real world images with diverse images and objects that are significantly more challenging than existing 3D benchmarks. This represents a new way to measure research progress in 3D and pushes the field away from a curated images synthetic assets towards real world perception and common sense 3D understanding. That's gonna be coming soon, so probably gonna be very remarkable actually. Amazingly, now you can use prompts to just say people and it will like segment people. If you say penguin, it will segment penguins. And this is where they merge the text encoder with this amazing visual model, and the amount of opportunities and things here you can do is just gone through the roof, and it's just remarkable how they are able to do it. So let's dive deeper into the paper and see what how they have actually achieved this. So this was the paper that was released by Meta, and as you can see, there's a bunch of authors involved in this paper, published by Meta Superintelligence Lab, uh, and yeah, great work. So they present the SAM 3D model, a generative model for visually grounded 3D object reconstruction, predicting geometry, texture, and layout from a single image. They essentially say they are able to break the 3D data barrier that we have discussed quite a few times, and that's the mode they are trying to say that this model has over any existing architectures in the computer vision space. So the two insights that made this architecture possible, as we discussed, is as humans, we can reconstruct or create synthetic scenes where 3D object models are rendered and pasted into images. While humans can't easily generate 3D shapes for objects, they can select the likely best 3D model from a set of pre offered choices and align its pose to the image, or declare that none of these choices is actually good. They have this whole pipeline that they have been using from SAM to SAM 2D and now SAM 3D. It's basically a training engine inference scheme that they have developed where they try to minimize the human annotators needed to actually make the data set to be able to train this model. And how they do it, they actually use existing tools which are maybe not as good, but they can do parts of the task in parts of the job to some extent, and then cleverly use leverage that to be able to generate, let's say, 3D objects in a clever way, just by automation. Maybe the accuracies are not good, but it will essentially pre-train the model to a very to a good level, and then they can bring in the annotators in the loop to refine the objects that are being generated by these existing automated tools, and then refine the objects, and that can itself be when go into the training process, and this whole thing is trained again with the corrected objects and the better quality masks, for example. And that's how they actually are able to leverage the existing tools to create this huge humongous data set, and also train in a much more efficient and a faster manner. That's the pipeline that they have been generally using. It's a three-stage pipeline. They generally train on like just pre-train on like existing objects, then they bring annotators in between a little bit, and then they train it again. And once this has trained on partially on the corrected objects, they train corrected objects, they pass this again iteratively through the loop, and the new generated objects are corrected again, and the hard cases, edge cases, are again solved and annotated by the annotators. And that's how they're able to iteratively refine and create really nice mesh models, which look very idealistic and close to an essentially like an artistic rendition, close to like an artistic rendition. So so these are their contributions. They introduced SAM3D. It's a foundation model for 3D that predicts objects, shapes, textures, and poses from a single image. They have released the code, model weights, and demo, and they are going to stimulate further advancements in 3D construction and downstream applications for 3D. They have built a MITL pipeline, which is probably the same. It's just a fancy name of saying the same thing that I just mentioned of how they actually generated the data set in the first place and how they trained the network. Uh, and Yeah, they exploit this data with via LLM style transfer, LLM style pre-training and post-training in a novel framework for 3D reconstruction, combining synthetic pre-training with real-world alignment to overcome the orders of magnitude data gap between 3D and domains such as text, images, and video. Of course, this is a multimodal foundation model, so it has to include all these different modalities, text, images, and videos, and brings all this together in a 3D format. And they also release a challenging benchmark, SA3DAO. I'm pretty sure they're going to release it soon, as they mentioned on their website. So here is the problem that they're trying to solve. The act of taking a photograph maps a 3D object to a set of 2D pixels. Specifically, once we take a photo, essentially, a 3D object is mapped onto 2D pixels. And how is that done? It's CV 101, Computer Vision 101. We specify a mask in an image, I. Simple. So there's a screen, you captured the image, there's a projection of this object happens on the screen, and a 2D version of that 3D object is created based upon the camera angle and all the other parameters of how the camera and the object are oriented with respect to each other, what part it can see, etc. So, but there's a mask. Essentially, you can say like an object is multiplied with a mask, and that's the image that's being created here on the screen. So the idea is to be able to invert this map. Can you actually go from the map, right, to, if you can do M, if you know the M, you lose the M once you have taken the picture. The idea is to, can you actually invert this map, predict this map, and invert this map to be able to restore the 3D object that was there in the first place. So this is a generative approach. This is where the machine learning actually shines through. All these different tasks of super resolution, 3D reconstruction, all these 3D generative models actually bank upon this idea to be able to reverse engineer, that the model is able to learn through heavy pre-training, this inverse map where you can actually go back and restore some of the lost information. Let the object has a texture, shape, and rotation. Uh, Translation and scale, RTS in camera coordinates. Since the 3D to 2D map is lossy, we model the reconstruction problem as a conditional distribution, uh, probability of scale, translation, rotation, uh, texture, and scale, given the image and the mask. Can you predict all these properties with a high probability, given you have the image and the mask? Their goal is to train a generative model that approximates P as close as possible. So that's how we are formulating our problem. The architecture, albeit, is kind of simple. Uh, Once you kind of know how they actually do this stuff, they have a playbook that is played out generally almost in all multimodal modalities. Uh, multimodal architectures, and its playbook is played out very commonly in all the architectures across the board. So they use Dino V2, which was also released by Meta, which means distillation with no labels. So it basically, let's say you have this is an unsupervised, totally unsupervised, pre-trained labeling of objects based upon just seeing multiple different objects of similar kinds hundreds and thousands of times. And it can basically start to just seeing different objects, it can start to correlate with each other, that I've seen this object before and it looked like this. And we actually do not need any labels, honestly, to be able to do those classification. It might not know that we call it dog because there's no label, but it definitely knows that this thing I've seen it many times, and this thing is exactly what I've seen in the previous picture, which is a characteristic of a dog. So that was again released by Dino V2, and they use that as an image encoder to extract features from two pairs of images, resulting in four sets of conditioning tokens. So you have two pairs of images, they extract features. Uh, so they generate four sets of conditioning tokens. How? They have a cropped object. So they encode the cropped image I by mask M and its corresponding cropped binary mask, providing a focused high resolution view of the object. So they crop the image by mask M, and they basically crop the object. So you have a mask around the other objects, you mask that out, you have one particular object in focus, and they have a full image, which is the full image binary mask, providing a global context and recognition cues absent from the crop view. So essentially the idea is similar that they have used in the Dino V2 paper, which they have a global crop and a local crop. The local crop is essentially focused on one particular segment of the object so that you can learn local features, and then there's a global crop, which is you take a bigger area of the image, which generally represents the orientation of how the room is, or how the 3D objects are correlated with each other, how do they sit on each other, what do different occlusions even mean, stuff like that. And that is a global crop view, and it will help the model generalize and understand the context much better. So we need both local features and global features, and they bring this idea again back here from Dino V2, and they use a cropped object and the full image, and they have two such pairs. So scene 1, scene 2, and they do it on both. So essentially they have 2 into 2, 4 such pairs. That's why they say they have 4 sets of conditioning tokens. Uh, One second. So the model supports conditioning on a coarse scene point, P obtained via hardware sensors or molecular depth estimation, SAM3D to integrate with other pipelines. Yeah, so there's possibility to do all this stuff. Um, okay, so this is the training paradigm we're talking about. Uh, we can go deeper into that later, but essentially it's the same thing that I was mentioning. Uh, the geometry model, the geometry model models the conditional distribution P object probability of object RTS given I and image. Object is the core shape, R is the 360 rotation that we have, T is the translation, S is the scale. So we condition the input and mask encodings. Condition the input and mask encodings. They have 1.2 billion parameter flow transformer with a mixture of expert architecture uh, of transformers, which models geometry O and layout RTS using the attention mask in figure 2. We can go deeper into that. And so this was the input encoding that we discussed. They're kind of going deeper into what models do they actually develop. So that there is a geometry model, there's a texture and refinement model, and then there's finally the 3D decoders that they have for different purposes. So there's a geometry model that's being developed, there's a texture and refinement model that's been developed, which is kind of new in the space, but we are operating with 3D, so we actually need geometry extracted out, and we need texture for that each of that object. So the geometry module models the conditional distribution of ORTS. So remember, uh, the probability that we were trying to estimate was P STR capital T R T S. Here, shape. So in the geometry model, we are essentially getting the shape, so essentially capital S, R, small t, and S. So geometry, so we are predicting four variables at once because they assume that they have a huge correlation among each other. They're able to predict all of this at once. So they're predicting four variables together, and they're predicting the texture variable as after you get this object. So you get the shape first, and then you get put the shape back with image and mask, and then you get the texture and probably the final shape S. So there's a core shape that they introduce in between. So in order to predict P S capital T R T S, they introduce that in because in order to predict the right object shape is hard directly. Texture influences the object shape and vice versa. They introduce a refinement module, which is they predict somewhat a coarse shape. Once you have that, you predict the texture, also the fine shape based on that texture. So that's how they're doing it. There's a geometry model, there's a texture and refinement model that's being developed here. Uh, how do they do it? We'll go a little bit into the architecture. This is the training that I was discussing about. So the pre-train builds foundation capabilities such as shape generation into the base model, uh, sometimes called continual learning, which is a mid-training phase. Uh, and there's a step two, which is post-training. It elicits target behavior such as adapting the model from synthetic to real world data, or following human aesthetic preferences. So essentially, they collect training samples, which is going from I and mask to STRTS and preference data from humans and annotators, which is used for fully supervised fine tuning. Uh, so these are the three phases that they use generally, very consistent across SAM papers. If you want a more deep dive into how they do it, I'll recommend you guys to check out my SAM paper, and we'll go deeper into that there. So one thing to note here is, like, as we're predicting five variables at once, pre-training helps to get some shape generation into the base model. Mid-training, which is some sort of like human in the loop coming now in the picture. It's continued pre-training. Mid-training imparts general skills such as occlusion, robustness, masked following, and using visual cues. And post-training is essentially fine-tuning, so that will be super nice. But it's expensive, so they have to do it at the end of the pipeline. So they're just saying that they have gathered a set of images, shape, texture T using 2.7 million object meshes from Observer's Excel, which is probably an open source library. And they also have some licensed data sets that they use. And they render each of them from 24 viewpoints, each producing a high resolution image of a single centered object. They call this dataset ISO 3DO, and train for 2.5 trillion training tokens, which is a huge amount. Uh, in the mid-training phase, they build up out the foundation skills that would enable the model to handle objects in the real world. So mask following, they train, what is mask following here, which is important. So they train the model to reconstruct a target object defined by a binary mask on the input image. So they train the model to construct the target object defined by the binary mask of the input on the input image. Occlusion robustness is, as if thing is being hidden by some other object, you're able to like still retrieve the right object with the right 3D model. And layout estimation, they train the model to produce translation and scale in normalized camera coordinates. So they're essentially able to deal with sizes and scale and the movement of the object, which is important in computer vision tasks. So they construct the data by rendering textured meshes into natural images using alpha composting. This render paste dataset contains one subset of occluded pairs and another subset where they replace real objects with synthetic objects at similar location and scale, creating physically plausible data that would with accurate 3D ground truth. They call this dataset RP3DO. So let me show you an example of how they do it. So if you see this picture, these are the initial isolated datasets, clean datasets that they initially use for pre-training, right? Then they have this RP3DO, which they are using. Now you can see this was a tree, and they pasted a truck on it, and there is a card on it. This is a picture where they threw a chair and some other objects on this particular image, and it's a 3D rendering. it's all good, but it just seems out of place. And that was the whole purpose of designing this designing this uh, designing this data set, which is occlusion based, and it it forces the network to learn the real 3D meaning behind the objects, and how does it circumvent and pass through the occluded objects to retrieve the right object. So they actually create this data set to like make things harder, but apparently make the model learn better features. So better features. So super important for this particular purpose. Same you can see here. Different objects are thrown, a chair over a building, and of different scale and sizes and shapes. So the model has to be able to generalize really well of how it's able to do this reconstruction. Uh, the MTL objects, we'll go that into a second. Into that a sec. Into go into that in a second. So this was the mid training, right? So masked following, they train the model to reconstruct a target object defined by a binary mask on the input image. So they threw a chair on the building. They have the binary mask of where they threw it, right? And they should be able to retrieve the object from that background essentially. So occlusion robustness, layout estimation, they train the model to produce translation and scale, of course. All right. They are able to create this physically plausible 3D ground truth or data augmentation essentially. In some papers they have a data augmentation module. It's data augmentation, where you can essentially augment the data and use your existing pipelines, automated tools to actually improve your output performance. We come to post training, which is the real world alignment. In the post training, they say they have two goals. The first is to close the domain gap between semi synthetic data and natural images. Second is to align with human preference for shape quality. It could happen that even just with closing the gap, that the alignment with human preference is not exactly the same uh, for how the object is reconstructed. So they actually aim at aligning the reconstruction with how the human perception is generally, or how the humans perceive it. It might be right, it might not be right, but that's how they chose to do it. And usually we see the world through our own lens, so we generally would take it uh, for how it is, how we see it. So they went to make it more comfortable. Their goal is to make it more comfortable and easy for us to visualize and understand the model. So they actually, it's in their favor. It only makes sense to do the alignment with the human preferences. uh, so they adapt the model by using their data engine iteratively. They first collect the training data with current model, and then they update the model using multi-stage post-training on this collected data. Then they repeat multiple times until it has saturated the to a high level of confident performance. So the collection, as we have discussed, the most people cannot create meshes directly because it's hard. It's like a skilled job. They require skilled 3D artists, and each object can sometimes take multiple hours. This is different from segmentation mask in SAM. So however, given options, most people can choose which mesh resembles an object in the image most accurately. This fact forms the foundation of their data collection for SAM 3D. Right here, they convert preferences into training data as follows: sample from post-trained model, ask annotators to choose the best candidate, and then grade its overall quality according to a rubric which they define and update. If the quality meets the evolving bar, the candidate becomes a training sample. Um, Unfortunately, at the first iteration, their initial model yields a few high quality candidates. This is because the first collection step, very little real world data for 3D visual grounding actually exists. So they deal with this with the cold start problem by leveraging a suite of existing learned and retrieval based models to produce candidates. Essentially the same thing I was saying. They use existing models to actually leverage the power of those models to be able to generate good candidates, and then they can build on top of that. So they don't need to reinvent the wheel all the time. So you can do that. In early stages, they just mostly draw the ensemble, but as the training progresses and their model starts to dominate in the performance, uh, eventually it produces about 80% of the annotated data set seen by SAM3D. So that accounts for about 80% of the annotated data. Annotated pipeline collects 3D objects, shapes, textures. Uh, so basically STR, T and S again for real world images. They streamline the process by dividing into subtasks, leveraging existing appropriate models and human annotators within each. Uh, yeah, sure. So that being said, they are able to essentially annotate almost 1 million images with 3.14 million untextured meshes and 100k textured meshes. Uh, Unprecedented scale for 3D data paired with natural images. So stage one is choosing the target objects. The goal of this stage is to, so this is still going in the post-training collection step. Stage one is choosing the target objects. The goal of this stage is to identify a large diverse set of images and object mask them to lift to 3D. They have to lift it to 3D. So what images and masks to lift to 3D is they have to select it. To ensure the generalization across objects and samples, they sample images from several different real world datasets, and they utilize a 3D oriented taxonomy to balance the object distribution. The reason is many times there can be a huge bias towards certain classes of objects that are seen in the dataset, and that would influence how your model learns textures and we do textures and spaces across different objects. So in order to like democratize the training, and in order to be able to do for in order for the model, in order to enforce the model to be able to be able to learn the right features and generalize, not just rote learn but actually understand, like generalize, uh, we generally democratize and make the distribution of objects unique across the board, or uniform across the board, standard technique that's used in machine learning. Stage 2, object model ranking and selection, ST. The goal of this stage is to collect image grounded 3D shape S and texture T. As described above, human annotators choose shape and texture candidates which best match the input image and mask. So human annotators basically select the shape and the texture. Annotators have a rating essentially. They, like for example R, they reject the chosen samples that do not meet a predefined criteria. Bad candidates are considered negative examples for preference alignment. uh, Data engine maximizes the likelihood of successful annotation and by asking annotators to choose between n equals to 8 candidates from the ensemble. So because many times the because of the orientation of the object, you can have different types of 3D meshes that can be generated. So that's why they have, instead of generating one proposal or two proposals or three proposals, they have 8 proposals that are generated, and they ask the annotators to choose which one is actually the right one. This is actually in conjunction, or in this is something that is in parallel to what SAM 2D or SAM 1D actually also does. So in SAM 1D, once we are segmenting any object, a particular object can have multiple different meanings. So if I click the pair of scissors, the object, the pointer that will land on the scissors, it could mean the handle, it could mean the cutting part of the scissors, or it could mean the whole scissors itself. So how do we know? It's ambiguous, right? But but only one of them is right. All of them are right in that context, but Sam wanted they wanted the network to know that all of these are correct proposals. So they actually output three different proposals for one point. Similarly here, they know that they use the same paradigm but in a in a different way. Uh, so they are able to they get this particular object, and they reconstruct the 3D object from that. The 3D objects can be multiple from different views. If you view that object from different views, it could have had somewhat a different 3D model representation, because you're at the end of the day just you're recreating data, you don't have the data, right? So uh, there could be some variation there. So they generate 8 different possible variants, and then they ask the annotators to identify which one is the best according to them. And that's why they're talking about human preference alignment. Stage 2.5, when no model actually produces a reasonable object shape, the non-specialist annotators cannot correct the meshes, resulting in a lack of data precisely where the model needs it the most. So these are hard examples, right? The model performs super poorly on these set of objects. So these need to be actually relabeled and uh, done properly by 3D artists that they hire for this annotation, and then this is fed back for refined training. And stage 3 is aligning objects to 2.5D scene. So the previous stages produced a 3D shape of the object, but not its layout in the scene. So we could create the object, but how big of the size it is, right, in the scene, how big, where it is in the scene, uh, what is the rotation in the scene, right? uh, I think R was rotation. What was R again? um, Rotation. Yes. So yes. So the alignment happens in the stage 3 of the post training pipeline, and it's about aligning objects to the 2.5D scene, so they predict the R, T, and S at the time of training. The previous stages produced a 3D object for the 3D shape of the object, but not its layout in the scene. So for each stage to shape, annotators label the object pose by manipulating the 3D object's translation, rotation, and scale relative to the point cloud. They find that the point clouds provide enough structure to enable consistent shape placement and orientation. This is something that they just say, but this is super important while designing any system. They probably tried different variants of how this model can be architected, and they probably failed a few times, but then they probably found that doing it in this step-by-step structure process, where they doing the RTS prediction later, once they got the object, they were able to get this RTS prediction better, compared to had they tried it to maybe predict it altogether or maybe before. So it's probably somewhat a trial and error game, but it also kind of makes sense that once you have the shape of the object done, then you just about it's just about the placement and the rotation of the object, It's not so much about the shape of the object, which is the main intrinsic part of what the shape is about. So kind of somewhat decoupled from what the object is and how the object is oriented. So it solves both what and where essentially. So now they have collected the data as an API that takes a current best model uh, and returns training samples, which is D plus, essentially positive samples with a quality rating, and a set of less preferred candidates that are all worse than the training sample. That's how they are gearing up for the final model improvement step. They have D plus and D minus, two sets of candidates, and in the model improvement step, SAM3D uses training samples and preference results to update the base model through multiple stages of fine tuning and preference alignment. Within each post training iteration, they aggregate data from all previous collection steps, keeping only samples where D plus is above some quality threshold alpha. As training progresses, alpha can increase over time, similar to cross entropy method for optimization. Their final post training iteration uses zero point 0.5 trillion training tokens, which is massive. At the time of post training start, it has only seen the synthetic data that we have discussed up until now. So the RP3DO essentially one-on-one mapping that they did, like sent 3D objects, pasted 3D objects, and then we're training on that. So until now, the model was there. Now the fine tuning has started. Uh, they begin fine tuning on aligned meshes from stage 3. They begin SFT, supervised fine tuning, with noisier non-expert labels. They call it MITL3DO, followed by a smaller high quality sets from the 3D artist, which is the R3DO. The high quality R3DO data enhances the model quality by aligning outputs with artist human aesthetic preferences, or human preference alignment that we were talking about earlier. And this helps suppress common failures, floaters, bottomless meshes, missing symmetries, etc. And after fine tuning, the model can robustly generate shapes and layouts for different diverse objects and real world images. Humans are sensitive to properties like symmetry, closure, etc., and which are difficult to capture with general objectives like flow matching, which is the objective that they use to train this network. So the follow SFT with a stage of direct preference optimization using the D plus and D minus pairs, which is probably somewhat of a contrastive running framework. Uh, they found this off policy data was effective at eliminating undesirable model outputs even after SFT on R3DO. So, so once they have trained on the high quality real world data sets from these people from this sets, they also do some contrastive fine tuning at the end so that they actually give preference on uh, how the hard samples should be viewed compared to the other possible views of a certain object. And generally, these are hard cases, so that's fine. And the distillation, finally, to enable sub-second shape and layout from the geometry model, they finish a short distillation stage to reduce the number of function evaluations required during inference from 25 to 4. So they have done some distillation, probably produce a smaller model from that and from the bigger model. These are the experiments that they run. That's okay. That's all good. We can go a little bit deeper into the architecture that they have. So the model essentially has mixture of transformers here, and it takes image encoders. It has image encoders here. It also has a point encoder which you can take it, give it as inputs. It has two modules. First one is the geometry model that we were talking about, and second one is a texture and refinement model that we were talking about. Uh, and essentially, there's a lot of cross correlations that are happening because these are all different modalities. Like we are not just predicting shape, we're not just predicting features, we're not just predicting texture, we're not just predicting rotation, translation, etc. We are predicting all of them together, and they are, of course, they co-jointly define how an object looks like in 3D in the real world, right? So they are able to they are essentially creating a foundation multimodal framework, and of course there are some aspects like shape, which a core shape which dictates how the shape is, uh, texture would look like. So they introduce that in between, which is the object O. Uh, but more or less, they produce the O RTS, and then they use that to generate a texture. That's the general architecture of this entire framework. Uh, so they give an image, which is the input coming. They have the object mask that is coming, uh, and they have layout tokens. They have shape tokens that are coming in here, which is the pre-trained tokens that they pass. At the time of training, they generated this, so they pass it. Point map is optional. You can give it point map, like what point you have to select, but it will otherwise generate this image, and you have to give an image and object mask, and then it will do that. Uh, it goes into a mixture of transformers. Now, what is mixture of transformers? They show it right here. So they have shape token and they have layout tokens that are coming in. They have the key query value pairs for each of these. Then they do a multimodal self attention, which I was talking about. So because this is multiple modalities, we have to do self self attention on multimodalities. Uh, so we'll discuss in a second how do they do that. But we have the feed forward network after that, and cross attention between different modalities. So this is something interesting that's happening here, and yeah. So there's cross attention that happens here. So this is a mixture of transformers. Uh, a very interesting concept. We can go deeper into that later. But the self attention is working as follows. In query, there is a query and there's key, and they basically self attention does a key query self attention, because this is a multimodal self attention. So what happens here is the shape token and the layout token are appended, and they produce this basically n cross n grid, n plus m grid, and shape tokens attend to shape tokens, layout tokens attend to layout tokens, but we also want layout tokens to attend to shape tokens, uh, and that probably goes here here and we have already accounted that in the key value pair, so we do not go the other way around. We just go one way. So so key is query is the shape tokens, and the key is gonna be the layout tokens. So this is done, and this feed forward networks that is passed, and then there's full cross retention that happens here, uh, which is query and key will be two different modalities. We should discuss why multimodal self retention mask is needed uh, in a second. But this is the mixture of transformers that they use. Uh, they produce the layout. They have layout tokens coming out from here again, and then there's the shape tokens that are coming out, and they have layout decoder, which essentially finally a decoder that produces rotation, translation, scale, and there's a shape decoder that produces the shapes of this object of this object in terms of voxels. Uh, this goes back and is fed into the next module, which is the texture and refinement module. It again takes the object image and the object mask, and it takes the shape tokens again. It is again fed to the flow transformer, which is the same thing, which is not the same thing actually. This is a different transformer. We'll also dive deeper into this, and it also receives object, which is the rough coarse object shape from this geometry module. Once it goes into this, it produces a shape token here, and we get the mesh decoder here to produce the mesh, and then there's a Gaussian splat decoder which produces the Gaussian splat right here. So that's how it's working right now. So there's two things that we'll go deeper into: what is how these transformers are essentially working, and yeah, that pretty much sums up of how this paper is architectured. What are the different how this network is architectured, what are the different training paradigms, what are the different data pipelines and data training paradigms that are being used here, and how do they work in synchronously to produce the right object mask. As we discussed already, the inferences are nice. SAM 3D generally outperforms on all these different metrics. Usually F1 scores, IU scores, chamfer scores is down. So scene preference there, that they just we discussed in the main highlight of the white paper. Comparison with SOTA, they also have different data sets they use for pre-training, so they can test it again on for the inference. So SAM 3D is preferred 6:1 over prior SOTA, which is a huge leap in this particular field. They introduce a new real-world capacity to generate shapes and layout jointly, which was probably not possible before, and a sample and optimize approach, as in the render and compare approaches, can further improve performance. Another thing is like the strong results for layout and scene reconstruction demonstrate that SAM 3D can robustly handle both RGB inputs, which is SA3DI or LVIS preference set, as well as provided point maps. If you want to give it point maps, it can also work with that, so which is another huge feat. Post training improves performance fast, multi-stage training improves performance again. Other implications are of course given in this in their appendix, but that is pretty much how they are able to get this model working. And yes, this was the work done by Meta recently, and must I say it's a very remarkable work that will have a lot of downstream. We're gonna see a lot of explosion of research, as well as a lot of real world use cases in the near future. Uh, and I'm very excited to see how it's gonna evolve. That being said, let's dive just a little bit deeper into how uh, what is the mixture of transformers and what is a flow transformer, uh, right? So it looks like they do some flow matching distillation techniques to reduce the number of inference steps. So like they cannot naively do some distillation. They have some flow matching algorithm that they use, flow matching distillation technique that they use to do this process. Uh, Specifically, they adopt diffusion shortcut formulation, which offers several advantages over previous consistency distillation approaches. So probably they have a term for distillation self consistency, which is probably the same, the mean squared error RMSE style uh, reconstruction, and then they have this flow matching, which is taken from distillation papers or DDPM papers essentially, which is the hallmark of generating images based on diffusion models. And because they used to have huge 1,000 step pipelines, it was a very long process. So people have come up with shorter techniques to distill that 1,000 steps into 25 and still keep the high fidelity. So how did they do it? There's some flow matching techniques, and they borrow that principle from that domain to here to be able to distill the uh, the model effectively. Uh, it's called flow matching distillation technique, right here. Unlike the original formulation, they do not train shortcut models from scratch. Instead, we initialize from fully trained checkpoints, and they further refine them with shorter shortcut objective. So it's somewhat a different way of initialization and how they go about actually making it work in practice, essentially. Again, for preference alignment, they use some diffusion DPO, uh, which is some flow matching technique. Again, given the same input and image and a mask, they sample a pair of 3D objects uh, based on human preference, and this is the preferred object and this is the less preferred object, and the training objective is to like align with the human preference. Pretty much, they do it probably in the latent space, and this delta is probably fed again back to the network to correct itself. So VW essentially, yes. So VW and VL are the target flow matching velocities for the inputs, and V theta and VRF are the learned and the frozen reference velocities respectively. So they got the weak signal, they got the right signal and the wrong signal, and they use the velocity reference and the uh, learned velocities, and they basically subtract it from the learned velocity and the reference velocity, and take the RMSE of that essentially at different diffusion steps, it seems like. uh, and they they use this delta of the RMSE uh, to be able to do this alignment. Interestingly, so in order to train the geometrical model, they use rectified conditional flow matching as the, which is called RSFM, I think. RFM is a very CFM is a very fairly standard algorithm that's used. They use the rectified version of that, rectified flow matching. And yeah, so input image I am geometry module optimizes the following multimodal flow matching objective: expectation, VM minus V theta, right? Uh, M is SRTS. C is contains the conditional modalities image and mask. V theta is the learned velocity field for modality M at the partially noised state XT. They want to learn generate clean states and during training phases. These are ground truth 3D annotations for each modality. Okay, that's pretty much it. Texture and refinement module also uses the flow matching objectives using SLAT features. Uh, so shape LAT is probably like layout tokens, I think, and yeah, the object mask, the object ref object shape that they got. So pretty much it. Yep. that's how pretty much it. But then there are of course nuances to it, uh, which you can go deeper if it's needed. Let me know if you guys feel something that resonated with you and you wanted me to dive deeper into some of the concept, and I can make another video to go over that concept, and we can discuss more. So looks like our objective is done here, and we are able to fairly understand what this paper is about, what it enables, how it is architected, how it was trained, and what are the possible consequences and how it's going to impact us in the future. So I feel I feel great to be able to share my insights and my understanding of this paper with you guys. And yeah, keep in touch, and I'll see you on the next one. Peace.